Hi everyone, it's TK here, and I'm going to do a documentation video on the motor controller, this FOC motor controller. Yeah, and also because it's using like ADC, SPI, CAN, so it's also a good introduction video for how to use STM or how to program STM. Yeah. So firstly, let's have an overview of the motor controller. So firstly, we have a motor. And we have an encoder. To control the motor, we have a gate or like a MOSFET driver. Six MOSFET drivers. And we call this one the power stage. So there are three cables connecting the motor, and this is magnetic encoder. And also we have current sensing here. So in this motor controller, it's a simple shunt resistor, so we can measure the voltage across these. Okay, so here are the hardware components. Then we have the software components. So we have taking the current sense. We do. Okay, actually I forgot whether it's Park or Clark transform. Let's search it up. Or FOC control diagram. Okay, Clark first. So, with current sense, because we are sensing all three phases, we have IA, IB, and IC. And by performing Clark transform, we got I alpha and I beta, basically reducing the three phase into a orthogonal two phase current. And then we do, or I think this is inverse Park. Oh, okay, this is Clark. Clark or inverse Clark. This is Clark, and this is Park transform. So after Park transform, we convert the rotating frame, because we're sampling the current here, and it's a rotating sine wave. It's three rotating sine waves. And after transforming, it's becoming two rotating sine waves, but it's still rotating. So we want to decouple the rotation of the current reading, because sine wave, that's hard to control. So we get the encoder readouts that can tell what's the rotation of the rotor right now, and we do Park transform to get I, Q, and ID, and these two are then becoming DC values, two DC values. Okay, so here we have a PID controller that takes in the current and takes in a IQ, ID target current, and outputs VQ and VD, the voltage, desired voltage on these two directions. And then we do inverse Park to get V alpha and V beta, basically convert the DC values back to the rotating frame. And we also need encoder inputs here. And instead of an inverse Clark transform, we do SVPWM here. Basically, it's a fancy way to drive the 3 MOSFETs or 6 MOSFETs. So, like, we convert the voltage alpha, voltage beta to VA, VB, VC internally in this module, and then generate the PWM, like how much duty cycle should we do to generate like certain voltage on each phase. Yeah, so on this section is the current controller, and then we have another controller, that is the position controller, also a PID. So this one takes in the desired position and velocity, and also torque, the desired feed forward torque, into here and do PID calculation. Also, it requires the position and velocity input from the encoder, and outputs the target like IQ and ID. Okay, so basically what we need to know is, like, we have 5 components then in this motor controller: the position controller, the current controller, the power stage, motor, and encoder. Okay, so program-wise, we need to keep track of this 5 like sub-modules. Okay, and let's see the code. So here's the code structure. May not see, it's auto-generated by ST's HAL library, or like this IDE. It's all auto-generated, and because it's auto-generated, it's very long, and like every time you change the IOC file, it will change here. So I don't like writing like my user code here because it's hard to find the code, right? So instead, main function is the main function, and instead of putting code here, I just create another file called app.c. So basically my application codes, and I have 2 APIs exposed to the inside the main file, which is app.init and app.main. It's very similar to like the Arduino code structure. Like here's setup and here's the loop. So this way we can have a clean separated user code file. Okay, so this is app.c. Here's the initialization file and the main loop. And because for motor control we need like real-time response to events, so we cannot put all the code in the main loop. So as you can see, like everything in main, it's the non-critical functionalities. So update service, this is an exception because like in this one we need to use HAL delay function, and that's not compatible with the interrupt routines. So we need to put this in the main loop. And otherwise it's like some status LEDs and like debug UART printouts. So nothing critical should go into the main loop. And instead we handle events by interrupt routines. Where should I start first? Okay, so we have a global variable called controller, which stores all the status of this motor controller. And inside this struct, you can see there's the 5 components: encoder, power stage, motor, and 2 controllers. And they are defined in their own files here. Like encoder, it's defined in the header file. Like the count per revolution, the position offset, the filter alpha, and like all these info. It's backed up, or it's defined in the header file. And then we have some attributes that are belonging to the motor controller itself. It's the mode of the controller, the arrow status, the firmware version, and device ID, like the CAN device ID. Basically, I'm writing the code in a C++ fashion, but with C. So like you can imagine, motor controller is a class, and like mode, arrow are the attribute of the class, and then we have some methods of this class, except like it's defined by C functions. So every time we call the function, we need to pass in the reference to the motor controller, basically a pointer to that controller. And then we operate on that pointer to change the status of the controller or of those parameters. Okay, and let's see the configuration files then. So firstly, when creating a STM project, the first thing you need to do is select debug to be serial wire or like other, like or JTAG. It cannot be disabled because otherwise you lose the debugability of that chip after flashing your code. So that's the first thing to set. And then we do like ADC. So as I've mentioned, we have 3 channels ADC input that samples the phase current, and like the sampling needs to happen at a fixed time instant, because okay, this is getting complicated, because like for MOSFETs, for 3-phase inverters, like because okay, the schematic of the inverter is like this. You got, oh my god, this is big. You got 6 MOSFETs connecting in this way. So this is VDD, and oh wait, and this is ground, and these are the 3 phases connecting to the motor. And you have we can abstract it into like 3 pairs of input signals to drive the gate. So it's PWM here, and these are the current senses. So as you can see, it's connected to the low side MOSFETs. So only when the low side MOSFETs are open can you sample the current flowing through here, right? So we need to set the PWM, set the ADC trigger on this PWM control, so that like we need to sample here basically, or actually we are using center line PWM, so we need to sample here. And to do that, we need to firstly here are the timer settings for the PWM outputs. So you can see there's PWM generation channel 1, 2, 3, and then we have another PWM generation with no output. So this is generating the trigger signal for the ADC. And so we configure the timer to be counting up to 4000. This is like the value plus 1 is the reload value, so counting to 4000. And then for channel 4, we are setting the pulse to be 39998, basically one less than the threshold. So because of that, the timer counting is like this, right? And then the channel 4 will actually be triggering on actually, yeah, I draw this wrong. It's like this. Wait, how did I draw it? It should be like this. Yeah. So channel 4 counter will actually generate the PWM plus something like this. And then we can just hook up the ADC trigger to this edge. Like, then the ADC will sample at this edge and be able to read the current. So, here, timer 1, we set the trigger event to be output compared on channel 4, basically outputting this thing, this waveform. And then in the ADC settings, we do conversion based on timer 1 trigger out event. Okay, so now we have connected the two peripherals together, and it will trigger us at the correct edge. And we are using injected conversion mode because it supports up to 4 channels simultaneously, I think. Yeah, up to 4. Like if we're having more than 4, we need to use regular conversion then, but it's hard to use because like for injected conversion, it actually have 4 registers to store the converted result for 4 channels. But for regular injection, it only has 1 register field. And to be able to convert multiple channels, you need to use either interrupt or DMA to read out this value every time it finished conversion, and then like store it into a memory location. And that is hard to configure. So basically, if we're just converting 3 channels, we're fine using the injected conversion. Yeah, that's ADC 1 and 2. And because we are sensing from a shunt resistor, so the voltage is very small. And that's why we need to use the op-amp, the on-chip op-amp, to amplify the voltage before feeding it to ADC. So here's the op-amp. It's pretty simple, like we just configure the gain to be like 16 and then feed it to ADC. Like here we are sampling op-amp channel 1 with ADC 1 and then op-amp 2 and 3 with ADC 2. Okay, that finishes the current sampling part. Actually not. So for the code, in the initialization code, we need to activate the ADC conversion, and that is done in the power state init function. No, that is done where? Power stage start. Okay, still power stage. We start the PWM, and shouldn't we start ADC conversion? Motor controller init. Okay, let's see. Yeah, here. We start the PWM and then we start the ADC conversion. Actually, a better way to do that is reversely. Like we start ADC after starting PWM. But it doesn't matter. We don't need to pay attention to the first few ADC samples, it's fine. So we start the timer and also the op amp and also the ADC with the injected start method to start the injected channels conversions. And then we can just leave it there. And every time the timer triggers the ADC and every time the ADC finishes sampling, it will call into the actually I'm using a different method here. Yeah, so I'm doing it without interrupts because we only need the ADC reading when updating the commutation, and that's done every timer cycle. And thus, and also because ADC the values are kept in the 4 registers, injected registers, we don't need to worry about losing them, so we can just read out the values every time we need to read them. So I'm not using the interrupted method here, I'm just using regular conversion. The interrupted version should be, actually I'm not sure. I think there is a, injected start interrupt method. I'm not using that. So if using interrupt, we need to handle the ADC conversion finish interrupt here. But since we're not using that, we don't need to concern about that. To read the values, we can just, like in the update commutation method, we do it by getting phase current and like this method. It will just read out the registers. Yeah, that's ADC finished. And then we have normal timers for system tasks. In this motor controller, we have several time schedules. So the first one is, first one is update commutation, and that is happening at 20 kHz. Secondly, we need to update encoder reading, which is achieved by SPI, and that I forgot. It's controlled by timer 4, and that is 40. Okay, Python 160 divided by, or 163 ohms divided by 40 and divided by 1K. That's happening 4 kHz. And then we have main loop, which is a undetermined update rate. So for the 20K commutation stuff, we just hook it up to the PWM timer, PWM driver timer. So the driver timer, okay, firstly, the system clock, we are using 160 MHz system clock. And we need to divide everything down based on this. Okay, so for timer 1, we're setting prescaler to 0, so the timer, or the clock input to this timer is 160 undivided. And we're setting the counter period to 4K. So the frequency of this timer will then be like 40 megahertz, or no, 40 kilohertz, right? Yeah, 40 kilohertz. And then, but since every time we do the update commutation, we need to perform the FOC algorithm. Basically, we need to go all the way in this FOC computation loop, and that is expensive, so we cannot afford to do it at the 40K update rate. or actually we can with optimized code, but like currently we cannot. So we need to down sample it to 20k, basically in half, and that's actually like enough because we don't need anything faster. Yeah. So to do that, we're setting the repetition counter to 1. Basically, like it will like for the internal timer trigger, like it will trigger at a fixed time period, right? And this is 40k. And by setting repetition counter to 1, we're triggering at every other timer interrupt. So here, only at these edges it will call the interrupt handler code. Yeah, and that's how we get the 20k commutation loop. And the interrupt handler for that is like, so all timer interrupt will be called into this function, and it will pass in the timer handler, and we need to see like if it's timer 1, then it's the 20k update rate, and then we do update commutation. And then in here we like get encoder position, calculate the trigonometries, get the phase current, update it, and then okay, so this update, it's the FOC calculation. Oh my god, it's the FOC calculation, right? Like the Clark and Park transform, and inverse Park, and then inverse Clark SP PWM to the gate output. And then we set the bridge output based on the result. So this is update commutation, which is running at 20k hertz. And then we have another timer that is keeping track of the encoder reading, which is happening at 4k, and we are using timer 4 for that. So for timer 4, still the system clock is 160, and because the prescaler is 39, so the value is 40, like 39 plus 1, 40. So the input clock of the timer will actually be 160 megahertz divided by 40. So that's how much? 4k. Or 4 megahertz. Yeah. And then we are, the counter threshold is 1k. So we further divide it down by 1k, which equals to 4k. And that is handled also in the timer interrupt here, like motor controller trigger position update. And inside this method, we are triggering, okay, firstly we do a state conversion. So there is an internal state machine in the motor controller implemented by like if-else logic instead of a state transition logic. But, well, it basically see what the current controller mode is and then enable or disable the power stage based on that for safety reasons. And then we trigger the encoder update, which uses the SPI method. Okay, so SPI, it's in the connectivity here. So we can choose to use the hardware generated clock or chip select signal, but it's bad because, well, ST, I don't know what they are thinking when designing the firmware, but apparently you need to enable the SPI peripheral to activate the chip select signal and then disable the entire SPI peripheral to raise the clock select or chip select signal. And that is slow. That is very slow. So instead, we're using a GPIO to drive the CS pins. And also, this can enable us to have multiple CS pins for multiple devices. Yeah, and because we are reading from an encoder, like we need to set the SPI settings based on the encoder's spec. So it's 16 bits MSB first. And for clock, because we are using 160 megahertz clock, we divide it down by 16 to get a 10 megabits per second SPI transaction, which is the maximum specified for the encoder. Yeah, and the clock polarity and clock phase, these are just copied from the encoder's datasheet. Yeah, and NSS signal type is software. And we need to activate interrupt for this peripheral because we are triggering it. So SPI transaction, it takes time. So, and also because we're already in the ISR routine. Okay, so every normal Hall peripheral method, it requires you to input a timeout, right? And that timeout is counting the system tick. Like basically it's seeing the system tick, and like if the tick increases to some threshold, it will determine like it's timed out and like exit with the error state. But that system tick, it's incremented by this interrupt handler, which is like at the lowest priority. So actually inside any ISR routine, the system tick will not be incremented because like you are in a higher ISR routine than the system tick ISR. So you cannot use any polling functions inside the ISR routine. Well, the other way to solve this is you can raise the system tick handler, like to raise the priority, but like then you are risking of getting interrupted inside your ISR multiple times to update the systic, and your entire ISR will be slower, and that's bad. So because of all these, we cannot use polling method, so we need to use interrupt, and by the way, it's good anyway. So in the trigger position update, we are triggering the SPI to initiate a transmit receive frame, basically sending the command and also receiving the data at the same time. And here, before calling that, we are lowering the CS pin by this GPIO function. Yeah, and upon receiving the SPI frame or like finish transaction, it will be called into this ISR routine, which is the transmit and receive complete callback. And here, the first thing we want to do is to raise the CS pin to finish this SPI transaction, and then we can update the updated readings and all those. Yeah, and by the way, the frame buffer, the SPI frame buffer, it's stored in the encoder struct here. So like after the SPI completion interrupt, we can just read the buffer from here. Yeah, and that's SPI. And I just noticed that I have another periodic event of safety features. Basically, because this is a motor controller which is driving a motor, we want it to be under control anytime we're using it, or anytime the motor is activated. Or in other words, if we lost the communication between this motor controller and the host driver device, we want to disable the motor. And that's implemented with this timer, the timer 2, like the system timekeeping timer. What we're doing is, so timer 2, it's set to a pretty small or like a pretty slow update rate. So 160 megahertz divided by this thing is 10K, and then further divided by this. No. 10k and then 10,000. So it's 1k. That's one tick? No, I think there's something wrong. Wait a second. This is in hertz, and then divided by this thing, and further divided by 10k. Okay, so it is 1 hertz. That's weird. That's pretty weird. That's very weird. Why? Why is 1 hertz? That's too slow. Or is it timer 6? It's timer 6, right? It's timer 2. Oh my god, a bug found. Okay, let's see the can frame. Okay, but anyway, how it works is like it receives the message. So there's a heartbeat frame sent by the host devices every fixed period, like a CAN heartbeat frame. Where is it? It's here. Heartbeat. And every time we receive the frame, we set the counter to 0. Like basically we reset the counter. And this way the counter will not count up to the trigger threshold value and then send out the interrupt. And then we are good. Okay, I see why. This should be 1 second. This is the trigger level. So like if we are not receiving the data heartbeat data for 1 second, we're going to enter the ISR routine. Okay, that makes sense. So like this line, the timer 2 will only generate the ISR interrupt if it haven't been resetted by a heartbeat frame for like 1 second, and then I will enter here, and we basically set the motor to like disable the motor and set the arrow to be like timeout, like we are not receiving anything from the host. Okay, so that's another scheduled event, basically a timer implementation of Watchdog, because like ST, it has Watchdog, but it's software Watchdog. Or like the only way the Watchdog can be functional is it will reset the entire device, and we don't want it to reset the entire device. Yep. That's timer. And then finally we have the FD CAN FD, or like normal CAN. Basically it's the same. I'm configuring this FD CAN to be compatible with CAN 2.0. So it's basically normal CAN. And so for CAN configuration, there's something about the bit timing. Basically we want to keep the time segments to be as close to as 87.5% as possible. So this is segment 1, segment 2. And here we are using a 7:2 ratio, which should be pretty close to this value. Yeah, and then we set the prescaler to have the 1 megabits per second CAN communication speed, which is the maximum supported by CAN 2.0. Yeah, and we are also using interrupt to receive the CAN frames here. So in app init, when initializing the motor controller, we are configuring the CAN filter and then starting the CAN frame. Okay, one thing about the CAN ID or CAN filter is like I'm dividing Okay, not this method. Here. I'm dividing the CAN frame. Okay, firstly I'm using the stored version of the CAN ID, so it's 11 bits. And I'm dividing it to two fields, the functional data, or function ID, and device ID. Device ID is 4 bits long, and function ID it's like 11 minus 4. That is 7. So with 4 bits of device ID, we can support up to how many? 16 devices on the bus, and then we can have a bunch of functions for the function for this device. And what's good about this kind of partition is like then we can set the CAN hardware filter to filter out only the to receive only the message with our own device ID, basically the message that is sending to us, or the 0 ID, which is the broadcast message. Yeah, and like here we are basically configuring the ID to filter to be filtering on device ID. And actually we need to set the mask to like these lower 4 bits to activate the filter. Okay, that's CAN ID partition. And by calling the activate notification function, basically we are enabling the CAN interrupt. So anytime we receive a CAN message, we are going to be interrupted into this handler, which then we first read the CAN frame from the CAN peripheral buffer into our memory, and then we handle or like process that CAN message. So here we firstly separate the device ID and then the function ID. Okay, so here, because device ID can be either our device ID or the broadcast message device ID, so we need that. Okay, this is actually not needed if we are using hardware filter. I guess I'm only debugging the software filter, so here it's the software filter version. And then we extract the function ID. So we need to actually handle case by case different function IDs, which is defined here in this header file. Basically, we are separating the function ID still by the 5 devices, 5 sub-modules, and then we have some general CAN IDs. Yeah, and because we are using RESTful API, kind of like RESTful API for the CAN communication, we can have a get frame or a set data frame. So for get frame, where the host is actually requesting the data from our motor controller, and the identifier of the get frame is whether either it's a remote frame or the data field is 0 sized. Okay, so to process the get frame, we switch it by the function ID and basically set the returning transmit frame data to be whatever the host is requesting from. So all of these. And also because TX frame is a uint 8T buffer, so anytime we need to set different types to it, we need to convert it to the corresponding typed pointer and then assign the number. Yeah, these are the get requests, and then we transmit the CAN frame back to the host device. And otherwise, it's a put data frame. So the host is actually setting the parameters to be certain value in our motor controller. So here, still we switched it by the function ID and then set the corresponding states. And yeah, okay, special cases like for mode handling, basically state transforming. And also there's a flash control, so we are able to store or load our data from the local flash, because we want to store something after power off. So here's how it does it. Okay, the magic happens in the store config function, because for flash devices we actually need to erase it and then to program it by double words. So here are the functions to do that, but that's not important. Back to hello cam message. Another kind of like special frame is the heartbeat. So here we are directly setting the counter back to 0. So we don't need to buffer this data anymore. Yeah, and that's basically the entire motor controller. Okay, see you.